So this video we're going to focus on the foundations of equilibrium. We're going to talk about different types of equilibrium reactions that we're going to focus on in this course. We're going to talk about some of the foundations related to equilibrium constants and how that relates back to our equilibrium expressions, as well as a connection to thermodynamics. So first, let's go ahead and just start with a reaction here. We have this basic reaction where we have calcium carbonate reacting with hydrochloric acid to give us carbon dioxide, water, and our calcium chloride. So as this reaction is happening, we see this is an equilibrium reaction. Our products could be favored, our reactants could be favored, depending on what our K value is. But let's first start by writing out our K expression. So we can say our Kc value for this specific reaction is equal to the products raised to their coefficients divided by the reactants raised to their coefficients. So here we have carbon dioxide, calcium chloride, and reminding us that we exclude pure liquids and pure solids because they don't have a change in concentration no matter how much of them we have. If I have 1 milliliter of water or 1,000 milliliters of water, its concentration or number of moles per volume, moles per liter, would be constant. It doesn't change. So we exclude those as expressing them in our K expressions. So that would be a pure solid, a pure liquid. We do not exclude pure gases. And that's because a gas, depending on what its volume could be, it could have a different amount of moles in that volume because it depends on the pressure or the temperature or these other variables that we have. And so it's not a constant like it is per se with a liquid or a solid. So we have those as our products, our reactants. We have again here the pure solid calcium carbonate. So we wouldn't include that, and we would have our hydrochloric acid and squared again because we have a coefficient of 2. So that would be our K expression, and that tells us at equilibrium, once we've reached this steady state, right? And we mean by steady state that our concentrations are constant. So at equilibrium, there's a couple of things to remind us about. Number one, we have a constant concentration of our reactants and our products. Now again, this does not mean that they're equal, it just means that they are constant. They are not changing over time. But it also does not mean that we have our reactions stop. We still have reverse and forward reactions still are occurring. And so we still have, in this case, our hydrochloric acid reacting with the calcium carbonate and the forward reaction, and then the reverse reaction, we have the carbon dioxide water and our calcium chloride in that direction. Now, as we look at each of these reactions, what we'll see is that the relative amounts of our reactants and products is expressed in our K value. Right? K value tells us at equilibrium what amount of products we have versus reactants. Okay, so that's kind of talking just generally for any kind of equilibrium reaction, we can express that, right? And if we look at our Kc value, if it's something that is very small, what that tells us, right, it's not negative. We can't have a negative because we don't have any negative concentrations. But if we have a very small K value, what that tells us is that our reactants are favored, or we have more of our reactants at equilibrium. Whereas if we look at our K value, if, again, this is an if it is very large, what we'll see here is that our products are favored, again, because this is the ratio of our products divided by our reactants. So what we see here is that the numerical value as well as the expression tells us something about our reactants and products once we've reached equilibrium. So that's kind of the foundation ideas that we want to start with, and then we're going to connect this to thermodynamics, and then we're going to talk about some specific types of reactions or K values that we can have. So now when we're talking about the thermodynamics and how that connects back to equilibrium, what I have here is an expression that relates our Gibbs free energy versus our standard Gibbs free energy. And again, that's at standard temperature and pressure. So that's at 25 degrees Celsius. That's at 1 atmosphere for all of our gases, a concentration of 1 molarity. So let's go ahead and 1 molarity for anything that is aqueous or that's a solute. We're going to see it's 1 atmosphere for any of our gas reactants or products, as well as a temperature of 25 degrees Celsius or 298 Kelvin. Okay, so that we have our standard delta G. Now, how might that differ from the actual delta G when we're looking at this? Well, that's going to differ depending on what the relative amounts of our reactants and products are. Okay, so if we look at our delta G, we remind ourselves, if this is negative, that means that our reaction is spontaneous, right? If it's positive, well, that would tell us as the reverse reaction is spontaneous, or the reverse reaction is going to want to happen. Now, how does that connect back to equilibrium? Well, that has everything to do with our reaction quotient, okay? So this is our reaction quotient. Think of it as the same expression as a K-value expression. The only difference is that our concentrations are not the equilibrium concentrations, right? So if I was going to write out the reaction quotient, Q, for my example reaction I'm looking at here, it's going to be the same thing. Carbon dioxide, calcium chloride, divided by our hydrochloric acid concentration squared. So the reaction quotient expression is the same. The only time that we think of, like, why do we talk about this versus equilibrium constant, is that our Q does not equal our Kc value. Okay, these are our values, so our numbers, when not at equilibrium. Whereas, if we are at equilibrium, our Q equals our Kc value at equilibrium. Okay, so now we have the ability to see, okay, we have this reaction quotient. This is going to tell us which way our reaction will be favored. Is it going to want to produce more products? Is it going to want to produce more reactants thermodynamically based upon the relative concentrations that we would have? And that would be whether the forward reaction is spontaneous, reverse reaction is spontaneous, telling us how much we're going to get for each of those. Are we going to form more reactants? Are we going to form more products when our reaction's occurring? Okay, so that's what our expression tells us. Now, one important thing to note is that at equilibrium, neither the forward or reverse reactions are more favored. Okay, so at equilibrium, it's not like we're going to take all of our reactants and make more products, or take all of our products and make more reactants. What we'll notice here is that at equilibrium, our delta G is 0, because we are not at this place where we're going to take our reactants and form more products, our forward reactions more spontaneous, or the opposite is true. And what is that? What is the consequence of that? Is that we know that at equilibrium, our delta G is 0. Well, if we make this value equal to 0 and we're at equilibrium, that means our Q is equal to our Kc. What we'll see here is that our standard Gibbs free energy is equal to RT natural log of our K value. Now what this does is this gives us a direct connection from the Gibbs free energy change for the standard state reaction, 1 atmosphere for gases, 1 molarity for ions, etc., and our K value. And so this will tell us if we have a really negative delta G, well then we're probably going to have a large K value, right? Because we have the ability to see the connection between that is our delta G, and we have this natural log of K that we would have here, okay? And we're going to unpack this a lot more. We're just talking through an introduction to these ideas, but we do have this connection between the thermodynamics and our equilibrium that we'd have for any kind of reaction that we would look at, okay? So we've talked about equilibrium constant expressions. We've connected it to our thermodynamics. And again, we're going to go a lot deeper in that a little bit later in this course. But now let's focus on a couple different types of reactions that we possibly could have and what that means for us when we're writing out these expressions, okay? So we have different types of reactions. I think this first one we're most familiar with, and that would be weak acid or weak base reactions. So for example, we have a weak acid reaction where we have our weak acid reacting with water to undergo ionization to give us the hydronium ion and the fluoride ion. Okay, we can also more generically just say RHA for any acid reacting with water to give us H3O plus, and now that anion, whatever that anion is. In this case, it's the fluoride ion. So we have these expressions here, and we see that we have the ability to relate our equilibrium to a specific reactant or product. But we can see here that we have, this is what we call our acid ionization constant, equilibrium constant. We have our acid undergoing ionization, so that would be our Ka. And we could write that for either one of these. So we could say the Ka for HF is going to be equal to, again, our products divided by our reactants. And again, we're excluding water as the pure liquid here. We can also more generically do this for every single equilibrium for a weak acid. And let's just say for HA, that's again going to be our hydronium ions, the anion, divided by that weak acid concentration. Okay. The larger that K value, the more products we get, the more H3O plus we get, the stronger the acid. Okay, that's just a reminder for us. Okay, so that's like a weak acid. We also can have a weak base. Okay, so if we have a weak base, if we look at a weak base that we would see, we can use a weak base that we experience all the time in nature, and that would be ammonia. So our ammonia is going to react with water. It's going to accept a proton from water to give us NH4 plus and the hydroxide ion. And again, we can make this very generic for any base. If we just say B is a base, reacts with water, and that's going to give us BH plus. So we just add H plus to whatever our original base was, plus the hydroxide ion that we would see here. And again, we can write out the Kb for, let's just do it for our generic base B, is equal to our products, BH plus hydroxide ion divided by whatever that base would be, that molecular weak base that we would have. So now we have the ability to see this for a specific weak base or weak acid. We also could possibly have like polyprotic acids, which have multiple acids that they can donate, acidic protons. So we have our polyprotic acids that we can have, maybe something like carbonic acid. So we have H2CO3 can donate its first proton to give us H3O plus and the bicarbonate ion. So we could label that for that first one, we call that Ka1. That's the first proton it donates. And then we now have that bicarbonate ion that now has the ability to donate another acidic proton to give us the carbonate ion. And we could call that Ka2. So that would be the second acid ion, proton that it would donate, the second acid ionization constant. So we have these two relationships that we would see here for that polyprotic acid. So now again, we have weak acids, weak bases, polyprotic acids. So our next one we can talk about is the solubility product, the Ksp. And this has to do with something, how soluble something is. And a lot of times we think about this in connection back to precipitation reactions. Now, normally when we write a precipitation reaction, we write it in a way where we take our reactants and they form a precipitate. So let's say, for example, we have a silver ion in solution combining with a chloride ion in solution to form solid silver chloride. So that would be like our precipitation reaction. Now, when we're looking at the equilibrium that goes along with this, a lot of times what we write, or what we're going to focus on writing, is how soluble this substance would be. So how much of the silver and chloride would be dissolved if I added silver chloride into water? And so instead of writing it in a way where we're looking at the formation of that solid, we're going to look at the formation of the ions from the solid dissolving. So we would have our silver chloride forming silver ions and chloride ions. And we call this equilibrium, the equilibrium constant for that reaction where this silver chloride is dissolving, the Ksp, and we're going to say it for specifically silver chloride. Okay, and we call it the solubility product. It's the product of the soluble ions that we would see for this solid dissolving. And it's going to be equal to, just like any other equilibrium constant expression, our products of our reactants. So here we're going to have our product ion concentration, silver chloride, and we would divide them by our reactants. Well, our reactant is a solid, so we would divide by 1 effectively. So what we'll notice is that it's just the product of the ions that we'd be forming when this dissolves. And this is going to tell us something about how soluble something is. Just like we talked about how strong or weak an acid something would be based upon its equilibrium constant, what we'll notice here is the smaller the Ksp, what that means is we have fewer ions dissolving. That would mean something would be less soluble, right? And the larger the Ksp, that would be something that is more soluble, right? So if, for example, we have these ions present, something with a really small Ksp value is going to be something that would precipitate out first because it's going to have the fewest amount of ions present that could possibly be in solution. So again, we have weak acids, weak bases, we have solids being able to dissolve when we're looking at a reaction. And so we'll see that this is another equilibrium type of reaction that we can focus on, and we will focus on this semester. And now the next one that we're going to look at is when we have complexation reactions. Again, we're just going through the basics and talking about some foundational nomenclature that maybe will help clarify some ideas when we're looking about these reactions. So we have precipitation, now we have metal complexation or formation reactions. So these metal ligand or formation reactions also tell us something about the equilibrium that goes on with maybe a metal ion in solution. And we're talking about a ligand. And a ligand is something that attaches to a metal, but is not necessarily forming this kind of 1-to-1 ratio to give us something that's neutral, like maybe we would see for our silver and our chloride that combine when we talked about our Ksp. And so here, sometimes it may be a metal ion with something neutral. It may be a metal ion with a negative ion that's going to complex in some way. And by complex, what we mean is that kind of one observation we can make is it leaves a charged species. So we're not necessarily changing the charge or making it neutral in a way that would make it possibly precipitate out. And so, like for example of this, is maybe we can look at Cobalt Ion Complexing with ammonia. So ammonia is a neutral molecule dissolved in water. Now, as it's dissolved in water, and again we have a cobalt ion dissolved in water, what we'll see is that it's not necessarily going to form a solid, it's not going to form this neutral ionic compound and precipitate out like we saw with our silver chloride, but they're going to form these complexes where they're going to combine in a way where effectively like the negative side of the ammonia molecule, the nitrogen side, is attracted to the cobalt ion. And so it's going to want to face it and interact with it, similar to the way we think of hydration for water. And when it does that, we consider that ammonia a ligand. Okay, so we have our metal, and then we have our ligand. It's something that's attaching to or being interacting with that metal ion. And so when it does this, it's going to give us a cobalt ammonia, and again, because ammonia is neutral, this is still a 2+ charge ion complex. Okay, and so we see that we have this formation of this complex, and we would classify the equilibrium constant that goes with this as a formation constant. That's what we call it K sub F. So this would be our Kc would be our Kf here for this specific reaction, and that would be our cobalt ammonia complex divided by our cobalt ions, and then our ammonia concentration, again to the 4th power here now because we have a coefficient of 4. And so we see here we have this metal ion that has the ability to form this complex here. Now we're going to unpack these a little bit more because we see that these actually happen in kind of like the stepwise manner, kind of like we think of a polyprotic acid. where we'd have maybe cobalt attached to one ammonia, then another, then another, then another, in these 4 stepwise reaction. But we can think of the overall equilibrium that's going on here is with the cobalt with those 4 ammonia molecules, especially if we have enough ammonia molecules to form this complex. We're always going to see that we're going to have competing reactions. And this is when we're going to focus on this idea of a system of equilibria. Okay, and when we talk about a system of equilibria, we introduced this in class already, is that it's all these different related reactions that they may compete with each other based upon their K value. And we're going to talk about how these interact with each other, how they contribute to each other, how they maybe block one reaction from happening because one is more favored. And we're going to talk about how there's a kind of a relationship between them, and that's why we call them a system, that helps us see, and especially in the natural world, that there's not just one reaction that just dominates everything. There's all these different reactions that have interrelated reactants and products, and we're going to look at how do we connect those to each other with these different types of reactions. So we may focus on a formation reaction and how that connects back to a Ksp or a solubility product reaction, a precipitation reaction. And we want to see how they connect to each other because one may be more favored than another, and we need to understand why, and we need to understand how we can predict whether one would be more favored than another. So hopefully this video gives us a good kind of background in thinking about equilibria, good background in when we mention these different ideas, how we can connect them back to equilibrium constants or these different types of reactions. And then we're going to get a lot deeper in these different topics. This is kind of a first exposure, and I look forward to that ability that we will have in class to kind of get deeper into each of these different topics, because these are important in the way that we analyze specific ions, because they may interfere in certain ways if we choose one type of analysis versus another.